Okay, so as usual, let's start with a review of our last lecture. Our last lecture was last Monday. So last week I talked about properties of Laplace transformation. Okay, so we first defined Laplace transformation, and we know how to take the Laplace transform of any function of time. It's just an integral we need to take. But I told you that we rarely take that integral to find Laplace transform. Instead, we use Laplace transform tables, and in those tables we know the transformation of some basic functions. But more importantly, there are some properties that Laplace transform satisfy, and these properties make it very easy to take transform of more complex signals. So we talked about those properties. So we said that, so maybe I should open the other file. Let's see. So these are the properties. So first two properties say that Laplace transformation is a linear operation. And then there's this differentiation property, which will, as we will see today, make our lives very easy. There's the integration property, and then there are time shift and complex shifting properties, together with these initial and final value theorems. And keep in mind that these are not the complete list of Laplace transformation properties. You can find some other properties that are less frequently used for this course, so that's why I didn't include any other property here. But if you want to do you use Laplace transformation for more complex problems, then you may want to take a look at or more detailed properties of Laplace transformation. Okay, and the last thing we talked about last week was this table. Okay, so this chart summarizes how we use Laplace transformation. So we start with a set of equations that describe a system, a physical system. So once we have the equations for that system, our goal is to analyze that system. Okay, so our goal is to find the response or the output of the system in time, and this could be the response to an external input applied to the system, or it can be response to some initial conditions the system was released from. Normally, we will have to work with these linear ordinary differential equations to get the answer. But if you use Laplace transformation, you can take the differential equations, and without solving them, you directly take the Laplace transformation of those equations. And once you have taken Laplace transformation, these equations turn into algebraic equations, and then you can solve those equations, and then you get the response in S domain. So here you have the response as a function of time, but in the other one you have the response as a function of S, and then you can go back to time domain by taking inverse Laplace transform. So this is where we stopped. Okay, so we have still some materials here, so we can continue from this file. Okay, so let's see how we do that on our simple example. Remember, this was the spring mass damper example, for which we have this second order ordinary differential equation. We're starting with finding the response to initial conditions. Okay, so on the right hand side we have 0, which means the initial there's no external input applied to the system. And we have these initial conditions. The initial position is y0, and the system is released with an initial speed of y0 dot. So from here we take the Laplace transformation of this equation. Okay, so we take the Laplace transformation of the entire equation. So Laplace transformation of the left hand side, and on the right hand side we have 0, so we don't have to worry about the right hand side. So this is what we need to transform: my double dot plus by dot plus ky. So here we immediately start making use of these properties. So if you remember the linearity property, so we can quickly go back and remember what it says. So if you have functions of time added or subtracted, you can take transformation separately. Okay, so that means instead of taking all these terms together, we can separate them. So I can separate these three terms, and then once I do that, I can take these constant terms out of the transformation, since they are just constant numbers. And this transformation of this term becomes equal to transformation of these three terms separately. Okay? So I have m times Laplace transformation of second time derivative of y, b times transform of time derivative of y, and then k times transform of y itself. Next, we make use of the differentiation property. Okay, so I need to transform these to three, y double dot, and y. So we go back to the differentiation property, and then we just use that directly. Okay, so this is the differentiation property. If you want to take transform of the nth derivative of a signal, so here's how you do it. You just put s to the power n times the transform of the signal, and then you subtract these terms due to the initial conditions. So I did just that, m times, so these terms in the parentheses here are for the transform of y double dot. This is transform of y dot, and now y itself. Next, I collect all the functions of all the ys terms together. I have s squared times ys here. These are s times a constant number, another constant number. b times s times y of s. Once I do that, here's what I have. So I collect all the ys terms on the left hand side, and on the right hand side I have all these terms which are all constant numbers except this s here, right? M is a constant number, y0 is the initial condition, y0 dot is the initial speed, and there is no function of y term on the right hand side. Okay, and then finally I can find y of s as in this relation. Okay, so y of s becomes all these terms on the right hand side divided by these parentheses. Okay, so if you look at this result, it is just a rational function of s. So on the numerator we have a polynomial of s. In fact, it is a first order polynomial of s, since the highest s term is s itself. On the denominator we have a second order polynomial of s, and these two are written as a ratio, so this makes it a rational function. Okay, so this is my answer. So if you release the system from a different initial condition, you change this y0 number here, or if you release it with a different initial speed, that will change the y0 dot here, but in the end the result is given by this expression, y of s. Let's see. Okay, so since we have a rational function here, this function has some poles and zeros. Remember that discussion. So poles are defined as the points on the complex plane that makes the function undefined. Okay, so these are the points that make the denominator 0. A second order polynomial has two such points, has two roots, and those roots are given here. So that y of s has two poles, which are these two numbers, and since the numerator is a first order polynomial, there is just one root, and we call the root of numerator 0. It has 1 0 that is located here. Okay, now if you want to see how the response looks like in time domain, you need to take this signal and transform it back to time domain. You need to take the inverse Laplace transform of this signal. Okay, so I hope that is explained here. Yeah, it says here that the response, to initial conditions can be found by taking the inverse Laplace transform of that signal y of s. Okay, so this is how you calculate the response to initial conditions. Next, on this example, we looked at how to calculate the response to external input applied. So for that, we need to put a signal on the right-hand side. So that is the next thing we do. So this time we assume that there is an input signal applied to the system. We call that f of t for the moment. And this f of t is on the right-hand side. So while taking the Laplace transformation, we need to take the Laplace transform of this signal as well. Okay, so for the moment, let's assume that the initial conditions are 0. So now we are taking the Laplace transform of this equation by considering this input with 0 initial conditions. Okay, so we don't have these y0 dot terms for this one. So the left hand side is this, and right hand side is the Laplace transform of f of t. Okay, let's just call it f of s for the moment. So from here we get the Laplace, the response of the function in S domain through this relation. So this part we divide the equation by this term. So the response is equal to f of s divided by this part. Okay, so this is how we calculate the response in S domain. So obviously we don't know what f is at the moment. If f is given, then you need to take the transform of whatever the input is and then put it here. Then you take the inverse transform of this thing together to go back to the time domain. So as an example, if you consider that the f is a unit step function, so if f looks something like this, at t is equal to, it jumps from 0 to some constant number. It doesn't have to be a unit step. It can be a step function. Then the transform of this, if you take Laplace transform of that signal, you get f of s is equal to f0 divided by s. So z1 is the number that makes this polynomial 0, right? So you equate this part to 0, and then from there you solve for s. So I hope this is correct. So the poles are the roots of the denominator, and zeros are the roots of the numerator polynomial. So for a step function, this is the response of the function given expressed in S domain. So if for unit step this is the response, but for a general step function there should be an f0 here. So instead of 1 you should put f0 here if you have a general step function. So this is again a rational function in S. This time we have a third order polynomial on the denominator, since we have this additional s multiplying the denominator. And there are no, or the numerator polynomial is just a constant number for this example. So if you want to check the response to a different input signal, instead of a step function, if the input is a sine wave, then what you need to do is you take the Laplace transform of this part on the right hand side, which is just this term taken from a Laplace transform table, and then put that f of s here, and whatever you get gives you the response in S domain. Okay? So the benefit of you doing this Laplace transformation is that whatever input you have, you take the transform of just input signal and then multiply it with this constant part, right? Well, the reason I say constant is this doesn't change with the input. So whatever you have here, this is just a property of the system. So this part is composed of the mass value, the damper constant, and spring constant. And this part doesn't change. If you change the input signal, only the term that multiplies it changes. Okay, so if you have sine wave, you put it here. If you have a ramp signal, you put it here. If you have any other signal, you put it there, and you calculate the function that way. So for example, I can ask you to find the response for this input signal, and I hope you can all do that. So suppose that the input applied to this system like this. So it is like composed of different steps. So if I give you this signal, so let's put some numbers here, and if I give you, you can calculate the response to this, right? So you can. So we did this in class before. You just consider this in terms of you divide this signal into different steps, and that will give you. You can take the transformation that way. Okay. So hopefully at this point you already appreciate how Laplace transformation makes this easier. So if you, for example, if you wanted to calculate the response in time domain, then you would have to take or solve this differential equation, right? My double dot plus dy dot plus ky is equal to sine AT. You would have to solve for this differential equation. But right now, all you have to do is find the transformation of this function and then put it into here, and then that immediately gives you the response in S domain. You need to take the inverse transformation to go back to time domain. Güzel soru, ona bakalım. So he's asking why we didn't take this part. So this part is due to initial conditions, right? So if you have an initial position, that y0 represents that initial position, or if you have an initial speed, then you have a non-zero y0 dot. But if you assume that the initial conditions are 0, then you take the transformation of this equation, right? So if you take the transformation of this equation with these initial conditions, this is what you get. If you take the transformation of this without the initial conditions, then all these terms will just disappear. And if you didn't have any input, then you would get so let's assume that the initial conditions were 0. Okay, so this is equal to 0 and this is equal to 0. Then taking the Laplace transformation of that equation would just give you ms squared plus ds plus k times y is equal to 0, and that just gives you y is equal to 0. But if on the right hand side you have an input function, if you have f of t here, then for that case, instead of 0, you have that the Laplace transform of that signal.
So because the initial conditions are 0.
Right. First, we assume that the external input was 0 and there were initial conditions only. And in the second case, we said let's assume that the initial conditions are 0, but instead we have an input to drive the system. But if you have them both at the same time, you can have an input function and initial conditions. Then what you have to do is you take the initial conditions into account while taking the transformation here, and on the right hand side you would have this f of s, and you can calculate the response that way. But since we consider them separately here, so maybe I can just quickly show it here. So if you had an external input in addition to initial conditions, then that external input would show up here as capital F of S, and then the response then would be equal to this plus 1 over right? So let me rotate here. If we had an external the response becomes this. And if you want to see how this looks like in time domain, again you need to take the inverse Laplace transformation and go back to time domain. Okay, so right now we can start talking about the transfer function. So transfer function is a very important concept and we use it a lot. So we, as controls engineers, we use this transfer function term a lot, so it's a part of our everyday life. And let's see how we define that. So for a general input function, for the previous example, we saw that the response in S domain can be found by multiplying this part with the Laplace transform of the inputs. So if you call this part g of s, this g of s never changes, right? You can apply different inputs to the system, and the different inputs will be changing this part that multiplies the g of s, but the g of s itself doesn't change. And as I said before, that g of s only changes if you change something in the system. For example, if you change the mass in the system, or if you change the spring and damper properties, this part will change, but otherwise it remains constant, and the input function only multiplies that g of s, right? So what I just said is already explained here, so let me just quickly read this. Note that the function g of s depends on the physical properties of the system and does not depend on input applied or the initial conditions of the system. This function is called the transfer function of the system. So it is a rational function of s, and it depends on the properties of the system. Okay, and how we use that transfer function is, if you want to find the response of a system to an input applied, all you need to do is you find the transfer function and take the Laplace transform of the input you're applying and multiply them together. Just with a simple multiplication operation, you can find the response. It is just as easy as that. Okay, so in time domain, this would require solving the differential equation for this input signal. But this, in the Laplace domain, you just take the transfer function and multiply it with the input to get the output. Okay? Okay, so here it says that in general, transfer functions always depend on only the physical properties of the system. For linear time invariant dynamic systems, transfer functions are always complex rational functions. So let's talk about this part a little bit more. And for that, let me go back to the other notes. And let me find that discussion. Okay, so if you have a general linear dynamic system, then whatever that system is, you can write the system equation in this form. Okay, so this could be a mechanical system, or that can be an electrical system, or it can be any other type of system, as long as it is a linear system. So the key term here is linear. Then the equation will be in this form. Okay, so you will have y, this represents the output, the input is u, and in the equation you will have some derivatives of the input and output signals, right? So depending on how complex the system is, you can have the first derivative, second derivative, and it can go all the way up to the nth derivative. And similarly, on the right hand side you have the input signal, but you can also have the derivatives of the input signal, and this can go all the way up to m, let's say. So this is how the system equation looks like. Okay, so since this is linear, you cannot have a combination of these terms, right? So you cannot have, for example, u and y multiplied together, or you cannot have y and y dots multiplied together, or you cannot have y squared, for example. So these are all nonlinearities, and these are not allowed. So you can only have these terms and derivatives, and they can be multiplied by some constant numbers. That's okay for a linear system. Okay, so this is the most general form of the equation. Okay, so it cannot get any more general than that. So once you have such an equation, and if you take the Laplace transformation of this most general equation by assuming zero initial conditions, so what you get is the following. So for the first term, you get a0 times, since this is the nth derivative of y, you should get s to the power n times the y of s, right? So remember that differentiation property. So in the differentiation property, for the nth time derivative, you get s to the power n times f of s, and you have a bunch of other terms, but these are all related to the initial conditions. And since we assume that the initial conditions are zero, the Laplace transform of the first term gives you this part. For the second one, you get a1 times s to the power n minus 1 times the Laplace transform of s. And you can do it for all the other remaining terms. N minus 1 times s times y of s plus an times y of s. So you do the same thing for the right hand side. You have d0 times s to the power m times the Laplace transform of u plus p1 times s to the power m minus 1 times u of s. And then you have all the other terms, and finally you have dm times the Laplace transform of u. And let me just put a small note here. To prevent confusion, we usually represent functions of time with small case letters and their Laplace transformations with capital letters. Okay, so we represent the y output system as a function of time with small case y, but once we take Laplace transform, that becomes a capital Y. So from here you can take left hand side into ys parentheses, and that gives you a0 s to the power n plus a1 s to the power n minus 1 plus an times y of s becomes equal to, and we take the right hand side into US parentheses, and that gives us B0 times S to the power M plus Bm times U of S. So from here we can solve for Y of S by dividing both sides with this part. So we can write the output of the system as you see here, and this part here is now the transfer function. Okay, so the output is given by the transfer function of the system times the Laplace transform of the input we apply to the system. So now this is our transfer function. Okay. So this really shows that if you have a linear dynamic system, then the transfer function of that system is always in this form. And this is exactly the form of a rational function. So you have a polynomial of S on the numerator, another polynomial of S on the denominator, and these are dividing each other. So the result is always in this form, in the complex rational function. Okay? Okay, so remember I told you that the key property here is that we assume that we have a linear system. Okay? So what happens if you have a system which is not linear? So let me just show you on an example why we strictly need linearity for this to be useful. So let's take a look at this case, which is a nonlinear function. Okay, so let's go back to our simple Spring-Samper system and suppose that that system is modified to be a nonlinear system. So we have y and y dots multiplied together, which is, as I said before, something that makes the system nonlinear. Okay, so now we have this nonlinear system. So let's take the Laplace transformation of this system. So let's take the Laplace transform of that entire thing. So I can write this as m times s squared times y, and I have b times the Laplace transform of that nonlinear term, y dot times y, and then I have k times Laplace transform of y is equal to the Laplace transform of input apply. So this is also obviously a function of s. Now I need to take the Laplace transform of this. Okay, so the two things that are both functions of time multiplied together. So you should be very careful here that you cannot write it as this. This is not correct. So the Laplace transformation is a linear operator, right? So if we have the Laplace transform of y dot plus y, we can write it as the Laplace transform of y dot plus Laplace transform of y. This is because of linearity. But we cannot do the same thing for multiplication. Okay, so this equality is not true. If you go back to the Laplace transformation properties, there was the complex convolution property. I don't know if I have that written here. Okay, so I have it here. The complex convolution property of Laplace transform states that the transformation is given by this relation. So if you need to take the Laplace transform of two functions of time multiplied together, the transform is given by this property. So you have the transform of these individual signals, capital F1 of S and capital F2 of S, and then you need to take the convolution of these two functions to get the transformation, and the convolution is an integral operator, right? So for this nonlinear system, if you take Laplace transformation, you end up with this integral equation, okay? And that is not any more simpler than solving the differential equation in time domain. So you take the Laplace transformation and you end up with an integral equation or a differential equation again. So that's why we use this Laplace transformation approach only for linear systems, and that is explained here. So for nonlinear systems, Laplace transformation does not give an algebraic equation. We still get an integral or differential equation even after transformation. And that's why Laplace transformation is useful for linear systems only. And similarly, the transfer function is also defined for linear systems only. So I told you that we talk about transfer functions a lot. And every time we talk about transfer function, we always indicates that our system is linear. Okay? So let's stop here for the break and continue after that.